Bismillahirrahmanirrahim. Welcome to the seventh lecture of Mechanics of Solids. In the previous lectures, we have discussed some of the basic concepts of stresses and strains. We have defined the different types of stresses present in the material and the corresponding types of strains. From now onwards, we are going to discuss how the externally applied loadings result in the generation of various types of stresses and strains in the members. We will begin our lecture with the definition of the Saint-Venant's principle. This is the principle on which the whole of the elastic analysis of structures rest. Basically, we can say that this is a very fundamental principle. And then we'll proceed towards the derivation of the equation for determining the elastic deformations in an axially loaded members. In the previous lectures, we have developed the concept of stress as a means of measuring the force distribution within a body and strain as a means of measuring a body's deformation. It is also well known that the mathematical relationship between stress and strain depends on the type of material from which the body is made. In particular, if the material behaves in a linear elastic manner, then Hooke's law applies, and there is a proportional relationship between stress and strain. Using this idea, consider the manner in which a rectangular bar will deform elastically when the bar is subjected to a force P applied along its centroidal axis. Here, the bar is fixed at one end with the force applied through a hole at the other end. Due to the loading, the bar deforms as indicated by the horizontal line, or the one's horizontal line, we should say. Now, the localized deformation that occurs at each end tends to even out and becomes uniform throughout the midsection of the bar. Like you can see here that the location at which the load is applied, we can see that the horizontal lines show a lot of deformation here and at this point where the bar is fixed. But this deformation is sort of even out or not very visible in the middle section of the bar. If the material remains elastic, then the strains caused by this deformation are directly related to the stress in the bar. As a result, the stress will be distributed more uniformly throughout the cross-sectional area when the section is taken further and further from the point where any external load is applied. For example, consider a profile of the variation of the stress distribution acting at section AA, BB, and CC. Now section AA and BB are close to the, as it is visible that they are close to the point of the application of load, and CC is further away from that point. Now if we compare the stresses that are acting at these points, we will come to know that there is a lot of stress variation at section AA. The stress is maximum at the point of application of load, while this variation is quite reduced at section BB, and then the stress is quite uniform at section CC. The minimum distance from the bar's end where this occurs can be determined using a mathematical analysis based on the theory of elasticity. Like this distance, this CC, can be determined using a mathematical theory of elasticity. It has been found that this distance should at least be equal to the largest dimension of the loaded cross section. For example, if this bar has a length of 18 inches and a width of 12 inches, then this section CC will be located at a distance of at least 18 inches from the point of application of the load. The fact that the stress and deformation behave in this manner is referred to as the Saint-Venant's principle, since it was first noticed by the French scientist Saint-Venant in 1855. It states that the stress and strain produced at points in a body sufficiently removed from the region of loaded application will be the same as the stress and strain produced by any applied loadings that have the same statically equivalent resultant and are applied to the body within the same regions. For example, if two symmetrically applied forces P by 2 act on the bar, the stress distribution at section CC will be uniform and therefore equivalent to an average stress that will be equal to P by A. This figure shows a rubber bar that has been stretched using by applying forces at its ends. We can see here that the distortion or the deformations at the ends are more even out in the center of the bar. Like the effect of this applied force is not very much apparent or very much distorted in the center of the bar. And this is in line with the St. Bernard's principle. We will now determine elastic deformation of an axially loaded member using Hooke's law and the definitions of stress and strain. Consider this bar, which is a cross-sectional area that gradually increases or varies along its length. The bar is subjected to concentrated loads at its end and a variable external load distributed along its length. This variable distributed load could, for example, represent the weight of the bar if it does not remain horizontal, or friction forces acting on the bar surface. Here, we wish to find the relative displacement delta of one end of the bar with respect to the other end. We will neglect the localized deformations that occur at points of concentrated loading and where the cross-section suddenly changes. From St. Venant's principle, these effects occur within small regions of the bar length and will therefore have only a slight effect on the final result. For the most part, the bar will deform uniformly, so the normal stress will be uniformly distributed over the cross-section. We'll take a section of this bar, a small section of length dx of this bar, and we'll draw, and this is the free body diagram of this cross section. The resultant internal axial force will be a function of x, since the external distributed loading will cause it to vary along the length of the bar. Like the resultant or the reactant force to this applied loading will not be uniform, but it will be actually a function of the length of the bar as shown in this free body diagram. This load will deform the element into the shape indicated by the dashed outline, and therefore the displacement of one end of the element with respect to the other end is actually d delta. Like for this small element, the displacement of one end of this bar with respect to the other end is actually d delta. The stress and strain in the element are then simply sigma is equal to p of x, this applied load, divided by a of x. Since the area, cross-section area, is also varying, so it is also a function of the distance x from the origin or from the beginning, and then strain is simply the change in length, which is actually d delta here, and the original length, which is dx. Using the Hooke's law, we have this stress is directly proportional to strain with the introduction of this constant of elasticity or modulus of elasticity. Putting in the equation the values for stress and strain, we come up with this equation of change in length, that is d delta is equal to applied force divided by, or the internal force divided by, cross-sectional area into the original length divided by the modulus of elasticity. What we actually needed to determine was the deformation of the one end of the whole bar with respect to its other end, and thus we can use integration of that small element to determine the deformation of the whole bar. This is the equation in the integral form, and here L is the original length of the bar, or the integration limits are basically uh, the one end of the bar and the other end of the bar, or the length contained between the two ends of the bar. Now we are moving towards a particular case from the general case in which both the load and the cross-sectional area of the bar was varying. In this particular case, or in many cases actually, the bar will have a constant cross-sectional area A as shown in this figure, and the applied load will also be constant P. For this kind of bar, this generalized equation in the integral form can be expressed as this equation, in which the load or the internal actually reaction force will be equal to the applied force P. It will not be a function of the length, and area is also not a function of length. So this complicated integral gets simplified to this simple uh, equation, simple algebraic equation, in which the change in length is actually equal to PL by AE, sorry. And if a sum of forces, or if multiple forces are acting on the bar, then the deformation will be actually the sum of, or the cumulative effect of, all the applied forces. In order to apply the equation developed in the previous slide, we must develop a sign convention for the internal axial force and the displacement of one end of the bar with respect to the other end. To do so, we will consider both the force and the displacement to be positive if they cause tension and elongation respectively. For example, in this figure, it can be seen that this force and this displacement will be considered positive because they are causing an elongation. While for this bar, which is actually fixed at the right end, this displacement and this force will be considered positive. Now we can apply the sign convention to this simple example. In this example, we need to define the deformation of this point A with respect to the point D. We can see here that we are actually having three three load changes, or three different points at which loads are changing. So we will have to take three sections as per the rules of taking sections or determining forces using the rule of sections, or the method of sections. We'll take first section here, and the second section where the load is changing, and the third section again where the load is changing. So if you are taking the first section, we'll arrive at this load of the reaction force of PAB is equal to 5 kilonewton. Then taking the section at this second point, we'll arrive at this load of PBC is equal to 3 kilonewton. And then taking the section at the third location, but then we are basically uh, using the opposite direction, like moving from left to right. We are going to from right to left. Thus, there will be no force at this in section PCD. Now, in order to determine the deformation of the point A with respect to point D, we can divide each of these forces with the corresponding areas and the modulus velocity, and then multiply this with the corresponding lengths of each of the sections, to determine the deformation of point A with respect to point D. Before moving towards the formal examples, let's revise the procedure for analysis for determining relative displacement between any 2 points A and B on an axially loaded member. First of all, we need to determine the internal force. For this purpose, we have to use the method of sections to determine the internal force within the member. If this force varies along the member's length, a section should be made at arbitrary location x from one end of the member, and the force is represented as a function of x. If several constant external forces act on the member, the internal force in each segment of the member between two external forces must be determined. Then the displacement is determined If the member's cross-sectional area varies along its length, the area must be expressed as a function of its position, x. If the cross-sectional area, the modulus of elasticity, or the internal loading suddenly changes, then the equation should be applied to each segment for which these quantities are constant. Okay, this is our first example, and in this example we have a steel bar, A36 steel bar, and it is made up of two segments having a cross-sectional area of 1 inch square and 2 inch square. We have to determine the displacement of this end A and the displacement of B relative to C. We can see here that the external loading is being applied at point B and point C. Then internal axial forces in regions A, B, B, C and C, D will all be different. These forces are obtained by applying the method of sections and the equation of vertical force equilibrium. In order to determine the internal forces, let's consider the first segment AB. The externally applied force is 15 kip, so the internal force at this endpoint of segment AB will be is equal to 15 kip. Now, at the endpoint of section BC, in addition to this applied load of 15 kip, we have two opposite forces of 18 kips. Thus, if we sum up these forces, this plus 15 kip to minus 8 kip, the force at this segment comes out as 7 kip, and it will be a compressive force or a downward directed force. At the third segment, or the segment CD, now the applied force, if we have now in order to determine the force at this and the internal force at this section, we have to take sum of all these forces, plus 15 kip minus 8 kip minus 16 kip. Now the force comes out as minus 9 kip. Using these internal forces, we can now determine the displacement or the relative displacement of the required points as shown in the next slide. Using the sign convention developed in the previous slides, which states that internal forces are positive and compressive forces are negative. Sorry, tensile forces are positive and compressive forces are negative. The vertical displacement of A relative to the fixed support D is we have to divide the plus 15 kip plus 7 kip, which was also a tensile force, and then the compressive force of minus 9 kip, and the sum of all these forces or all these expressions will be this tensile displacement of 0.0127 inches. Since this result is positive, the bar elongates, and so the displacement at A is upward. Applying equation for displacement between point B and C, here again the displacement was, or the force was, positive tensile force. So now the displacement is plus 0.00217 inches. Here B moves away from C since the segment elongates. In this second example, we are having an assembly of aluminium tube and a steel rod. An aluminium tube of AB of cross-sectional area 400 mm square is having a steel rod, or is attached with a steel rod having a diameter of 10 millimeter. If a tensile load is applied to the rod, we need to determine the displacement of the end C of the rod. We have to take the modulus of elasticity of steel as 200 gigapascal and the modulus of elasticity of aluminium as 70 gigapascal. Again, first we'll use the method of section, and if we divide this or if we take free body diagrams of the tube and the rod, we'll come to know that if we apply 80 kilonewton force at the end of the rod, it will result in a 80 kilonewton force at the other end of the tube. The rod is subjected to a tension of 80 kilonewton and the tube is subjected to a compression of 80 kilonewton. Based on this free body diagram, we'll now determine the displacement of the end C of the rod in the next slide. In order to determine the displacement of the point C with respect to the fixed end, we'll have to divide this displacement in two parts. First, we need to determine the displacement of point C with respect to the point B. Thus, in order to determine displacement of point C with respect to point B, we'll consider the length of this hole assembly, that is 0.6 meter, and the area of just this steel rod. And putting in this equation, we have arrived at this particular displacement of point C with respect to point B. Now, the positive sign indicates that the end C moves to the right relative to the end B since the bar elongates. The displacement of end B with respect to the fixed end A is now determined as using the length 400 millimeter, that is the length of the bar, and also the area of the bar, that was 400 millimeter square. From this, the displacement of point B with respect to the fixed end comes out as 1.143 millimeter. The negative sign indicates that the tube shortens and so B moves to the right relative to A. Since both displacements are to the right, the displacement of C relative to the fixed end A is therefore actually the sum of these two displacements, and it comes out as 4.2 millimeter. In this example, we are having a rigid beam AB that rests on the two short posts AC and BD. AC is made up of steel and has a diameter of 20 mm, and BD is made up of aluminium and has a diameter of 40 mm. We need to determine the displacement of point F if a force of 90 kilonewton is applied at this point. First of all, again, we need to determine the internal forces. The compressive force acting at the top of the post are determined from the equilibrium of AB. These forces are equal to the internal forces in each post. Like 90 kilonewton force is acting at this point AB, and since this is a rigid bar, so we can simply apply the summation of moment to determine the reaction forces at the end of this horizontal post or horizontal rigid beam, and these reaction forces are then the vertical forces or the compressive forces in the two vertical in the two vertical posts. Now the displacement of the top of each post is in the post AC. The displacement is determined using the length of AC and the area of AC and the force of minus 60 kilonewton acting at that particular post, and the displacement comes out as 0.286 millimeter. Similarly, for post BD, the displacement comes out as 0.102 millimeter. Now this diagram shows the beam AB and the displacement at its various points. Like the displacement at point A is 0.184, the displacement at point B is 0.102, and we need to determine the displacement at point F. Using the concept of similarity of triangles, we can determine the displacement at point F, like this 0.102 millimeter is the displacement or is the rectangular displacement, and then this for this triangular portion we have to take this ratio of the lengths, and from summation of these two displacements or you can say the to the summation of the two displacements, the displacement at point F comes out as 0.225 millimeter. This is our last example of this lecture, and it is a little bit complex because in this we are going to use the equation of varying areas. In this example, we are having a member made of a material with a specific weight gamma and a modulus of elasticity E. For example, this member is in the form of a cone having the dimension shown in the figure. Like this length is the length of the cone and it has a radius of r0. We have to determine how far its end is displaced due to gravity when it is suspended in this vertical position. The internal axial force varies along the member since it is dependent on the weight of the segment of the member below any section. Hence, to calculate its displacement, we have to use the equation with varying areas. Now we'll divide this seemingly complex problem in very simple steps. If we take a section of the cone at a distance y from its free end, we'll come to know that the radius x of this cone is a function of y and it can be determined by proportion. Like if r0 is the radius of the cone having length L, then this radius x of a cone having length y will be equal to x is equal to r0 divided by L into y. Now the volume of the cone having a base of radius x and the height y is this. This is simply an equation of the volume of a cone, and we are just putting the value of x which we have determined here. Now we know that weight is actually equal to the unit weight multiplied by volume of the element. Thus the internal force at the section becomes weight is equal to gamma into volume. Now we know the force at the section and we can determine the displacement by using the equation, the integral form of the uh, equation of displacements for the axial loading. But first we need to determine the area. Area will also be determined as a function of the position y. And now putting all these values in this integral equation, we have obtained this equation gamma into L squared divided by 6e, which is the equation for determining displacement at any point along this cone due to the weight of the cone. This marks the end of our today's lecture. Thank you very much for your attention. You can post your questions in the comment section. See you all in next lecture.